Hi there, my name is Christian Humbert from the company AbsInt, and in today's video I'd like to present a new static program analyzer called EnergyAnalyzer. The EnergyAnalyzer development has been co-funded by the European project TeamPlay, which is a part of the Union's Horizon 2020 Research and Innovation Program. What is EnergyAnalyzer? Well, it is a static program analyzer for energy analysis and to support development of embedded systems with energy constraints. It is based on the well-established AbsInt static program analyzer framework for binary level. And it is currently available for the ARM Cortex M0 and Leon 3 architecture. Using EnergyAnalyzer, you can detect an increased energy consumption in code snippets of your embedded application so that you can enable optimizations and save battery resources. You can also use it to monitor the energy consumption of your application in a continuous way and test different hardware configurations and check out the influence on the energy consumption. The EnergyAnalyzer workflow is similar to the IT worst-case execution time analyzer workflow. This is because major parts of the tool chain has been reused from the AIT tool chain, like the decoding phase, where you provide an executable program as an input to reconstruct the call and control flow graph in the first step, then followed by the value, loop bound, and control flow analysis phase. Newly developed has been the energy usage analysis step that calculates for each and every machine instruction its energy consumption based on a parameterizable energy model. This information about the energy on basic block level is given as an input together with the call and control flow graph structure to the final phase, the path analysis, which determines the worst case path with respect to the energy consumption. Let's have a demo on the EnergyAnalyzer now. First demo, I'd like to analyze a small data compression algorithm running on an ARM Cortex M0 architecture. By the way, the call and control flow graph you can see already here. I'd like to test out different hardware configurations of that M0 processor and check which of these configurations leads to an optimal behavior with respect to the energy consumption of that algorithm. For that, I have created different configurations in our EnergyAnalyzer here. The first one uses the default settings like having a disabled static prefetching of the flash memory and flash data wait states of 0. The next configuration, here we use a wait state of 1 cycle. Still the prefetching is switched off. The third one, here we enable the prefetching now and use a wait state of 0. And the last one enables the prefetching and uses a wait state of 1. Then I created 4 different EnergyAnalyzer items, all with the very same analysis start point, namely the main entry of that algorithm. I also selected different configuration here per item and provided a energy model. And now let's start the analysis of these 4 analysis items. And now you can see that we have a different energy consumption behavior as a result here. And if we sort here the result, we can immediately see that the configuration where we switch the prefetching on and have a wait state configuration of 0 cycles, we have an optimal worst case energy consumption for that small data compression algorithm. You can have an detailed inspection on where the most energy is spent or consumed, and you see in these compress sub functions, which I guess where we find some loops, the most energy is spent. By the way, this information can also be found in the statistics, where you have a tabular overview on the energy consumption. You can of course sort them here as well. The use case of my second demo example is slightly different. This time I'd like to energy analyze a software floating point implementation of the add function. I'd like to first find out where most of the energy is consumed, and to get some ideas on how to make, how to improve the energy consumption. For that, the first thing we see here is that most of the energy is consumed in the unpacking function here. Let's have a closer look to that. You see that there are basically 5 different paths through that unpacking function, processing the input floating point numbers. And why are there 5 paths? This is because you have basically 5 different types of floating point numbers. The first is the subnormal number. The second is just the null. The normal numbers, you can have not a numbers type, and the infinite type. And as you can see here is that most of the energy is consumed when you assume to have subnormal numbers. So if you now can guarantee that just normal numbers or the null is given as an input to the add function in your algorithm, you can exclude these other types which will never occur. And this is what I exactly assumed in my second run of the very same add function. This time, you see, the energy consumption is significantly reduced to just 42 microjoule, and well, if we now have a closer look to the unpacking, well then you can see that just basically 2 paths are remaining, the normal number path and the null path. All the others have been excluded or determined to be infeasible. This way you can save battery resources, right? That was already my short presentation and demo of EnergyAnalyzer. I hope you liked it. If you are interested in evaluate the EnergyAnalyzer, feel free to contact info@absint.com. Thank you very much. Take care and bye-bye.